grade 10s, and welcome to this lesson on functions. Now, it's been a while since we've seen each other, and a couple of things have changed, but mathematics always stays the same. And that's what's great about maths, is that no matter what kind of day you're having, you can just let it all go as you do a mathematical problem, and you don't have to think about the issues that maybe you have at home or with the person you like or whatever. You can just sit down and enjoy the numbers. Now, before we get too involved in functions, I'd like you to take a look at our challenge question for this week. So the challenge question for this week says the graphs, and let's scroll down a little bit, the graphs of y is equals to x and y is equals to 8 are shown in the following diagram. So we have y is equals to x, there it is. And then we've got these funny curly ones, which you might have already done in class, there and over there. And those two are linked to the y is equals to 8 over x. It's a hyperbola. It's just the straight line in pink and the hyperbola in purple. Now, in the question, we are asked to calculate the coordinates of A and B. So if we look over here, there is A and there is B. I don't want to give you too many clues, but just take a look at what's happening at those points. Anyway, the next part says, find the length of CD. Now, C is drawn from the perpendicular of B, or plotted at least, and D is plotted from the perpendicular of A. Then calculate the length of AB. Where is AB? Oh, it's this over here. So there is the length of AB. And lastly, find the length of EF if G is in the point 02. And where is EF? EF is over here. Okay, so grade 10s, I hope you've copied that down while I've been talking through it. And you'll also find it on the notes, but it's a good thing for you to try yourself. Now let's go to the first link, or the first slide, that's going to start telling us about the concept of functions. I've chosen to talk a little bit more about the concept of functions before we start plotting. And of course, the plotting is the focus of this lesson. Okay, so on the first slide, we have a function is a relation from a set of inputs to, let's underline inputs, to a set of possible outputs, where each input, there it is again, is related to exactly one output. Okay, grade 10s. Now this is really complicated in terms of a definition. And so we need to start thinking about it in terms of real life. What is it saying in English? Not what is the maths, what is it saying in English? And the thing it's saying in English is that you're going to put a number into a function. So you're going to take a number and you're going to substitute it into a mathematical statement of some sort. And you're going to get another number out. Now, the number you got out, your output, has a relationship to the number that you put in. And if you were to put a different number in as your input, the output you would get would be different from the first output, but it would have the same relationship to its input as the previous one did. Now, it can be quite difficult to understand why functions are important. Most people think functions are just the graphs, and that's not true at all. Functions talks about any relationship of any numbers to any other numbers. Now, because we've just come out of the Easter season, I thought of a great example to use for this. And the example is all about Easter eggs. Now, as you can see, I enjoy my Easter eggs, and I might have eaten a couple too many while I was over the weekend. And I did work out that, if I eat 5 a day, I'm going to gain roughly 200 grams by the next morning. Okay, so there we go. 5 Easter eggs equals 200 grams weight gain. What's the relationship? Well, if I don't eat the 5 Easter eggs, I don't gain the 200 grams. So my input is the Easter egg I'm eating, and my output is the amount of weight I'm gaining. And based on that relationship between those two numbers, I can then estimate how much weight I would gain if I ate 10 Easter eggs. Now, I would feel sick, there's no doubt about that. But if I had 10 Easter eggs, I'd gain 400 grams. And if I were to eat 15 Easter eggs in one day, can you guess how much I would gain? 600 grams. And that's assuming that this function is on a straight line. In other words, for every Easter egg I eat, I'm going to gain the same amount of weight every time. I don't know enough about weight gain to tell you whether it is a linear function or not. I can just tell you my experiences. Okay, so that is what a function is. It's a relationship between what you put in and what comes out. And it's actually everywhere in real life. Now, there are 4 different ways to represent a function. And we're going to look at those now on the slide. The first way is to represent it verbally. Now, a great example of the verbally is my Easter egg. Let's draw an Easter egg. This Easter egg has a stripe on it, and it's going to taste delicious. So verbally, we're talking about 5 Easter eggs equals 200 grams weight gain. And there's a nice function. Okay, now algebraically is when we write it as a formula. Y is always the output. Why is it the output? Because it's the answer that we get at the end. And X will be the input. Okay, so with this function, I have to eat 5 Easter eggs, and then I gain 200 grams. And I could change that into an algebraic function. What do I need to multiply x by? Well, we would figure that out to get to y, and we'll get to that later. Now, numerically, it can be represented as a table. And I'm going to draw a table like this, where I have my x on the one side and my y on the other side. You may have drawn tables like this, where your x is on top and your y is on the bottom. Both of them are perfectly correct. Now, in my case, I ate 5 Easter eggs and I gained 200 grams. I eat 10 Easter eggs and I gain 400 grams. And so on and so forth. Another way to represent this numerically is something you've probably seen before, which you've been doing since grade 1. And I hope that you all got excited as soon as you saw this. When I was in grade 1, we used to call these spider diagrams. So I would have the 7 over there, and I would say, okay, let's put in an input of 3, and it goes through the function machine, and it comes out as, what is 3 plus 7? It's going to be 10. So that's just another way. Another way we can represent it numerically, and let's just get rid of the table over here, is by doing a mapping diagram. And a mapping diagram has the inputs and the outputs listed in 2 different circles. Now in this case, we had an input of 5, and we have an output of 200. And that input links to the output that's over there. Okay. And in each of these, you will see that for every x value, we only get one answer for y. Otherwise, it's not a function. Okay, the last method we use to represent a function is graphically. Now, grade 10s, many people think that functions are graphs. And in the section functions, we actually only really focus on the plotting of graphs. So it's understandable that people think that functions can only be graphs. But the truth is, you've actually been working with functions since the very beginning of your schooling career, when you did those spider diagrams. A function is any set of relationship between an input and an output where you only get one answer for the output. If you get two different answers for the output, then it's not a function, then it's just a relation. But that's something you'll do more of in grade 12, that kind of definition. So when we plot functions, we're going to get different shapes. And the shapes all depend on how the x is being treated within the function. With some functions, as the x value goes up, so does the y value, and they go up in the same proportion. That means that we're going to get a straight line function, showing that one is going up and one is going across, and it goes across like this. Now, the other type of function we can get is as the x value goes down, the y value goes up. Or maybe as the x value goes up, the y value goes down. And you'll have seen a function that looks very similar to that kind of function. In fact, it is half of the function in grade 9 and grade 8 when you did indirect proportion. As the one value got bigger, the other value got smaller. Do you remember that curve? And then it never ever touched the x and the y axes? That was the hyperbola. Okay, then we've got a parabola where our input function is being squared. So it's a quadratic function. The input function is squared, so we have almost a smile that's developing, or in some cases, a frown. Okay, and the last one is an exponential function. An exponential function will either go up forever and ever and ever, or it will go down forever and ever and ever, or it'll come down like this, or go like that. It goes all over the place. Okay, but we're going to go into those in more detail in a little while. Let's look at what the rest of the key concepts are talking about. The next one says a graph is a function which has been plotted on the Cartesian plane, and that's exactly what we've just been talking about. We are taking the function, let's say we were to take the spider diagram function and plot it on a Cartesian plane, we're going to have a straight line that goes up. Why? Because all of our values are going up. The x value, the input, and the y value, the output. Okay, the next point says, function notation is a method of writing algebraic variables as functions of other variables, and that's important. Functions of other variables. Most often, functions are portrayed as a set of coordinates, and of course you know how coordinates are formed. Let's put a coordinate over here. This would be 3 and 10. With the vertical x-axis serving as function of x. For example, writing f of x is equals to 3x is the same as writing y is equals to 3x. And I'm just going to slip in that 3x over here so that it's on the same line. But that's it. Now, grade 10s, many people look at functional notation and they get a little worried. They're like, what is this foreign language? I know y is equals to mx plus c, but now you're telling me f of x is equals to something, something, something. You don't need to worry. F of x is very similar to saying y is equals to. Function notation is actually really, really useful. And I think a lot of our problems, we're going to write it as in the form as y is equals to. But maybe we'll play with things a little and change it to f of x is equals to, just to show you how useful this can be. Okay, so how are you feeling? You feeling good so far? Are you ready to plot a parent function? Let's go to the next slide and see what function we're looking at. We're going to look at the linear function. Now you'll know that the linear function is either written as y is equals to mx plus c, and that's probably how you did it in grade 9. But in grade 10, we also use the formula y is equals to ax plus q. Okay, both of them are exactly the same formula, except instead of an m, we now have an a. And instead of a c, we now have a q. So those are still the y-intercept, and these are still the gradient. Okay, grade 10s, before we plot that parent function, I'm going to let you have a bit of a break, and then we'll come back and be ready to do this. Make sure that you have your calculator on you, as well as a pen and paper, so that you can plot the parent functions as I'm doing it. See you just now. Okay, grade 10, so you're feeling relaxed and ready to get back into this. Now remember that a parent function is the function that is drawn when there are no changes to the value of a or to the value of q. So that means we're going to draw the basic graph. And in this case, the parent function of a linear function is going to be y is equals to x. So for every value x has, y will have exactly the same value. That means if x is equals to 3, y will equal 3. Or if x is equals to -7, y will equal to -7. It feels a bit pointless plotting this, doesn't it? But it will help us with our next lesson next week, where we have to change the values of a and q. Okay, I hope you've got your calculators, because I'm going to show you how to use the table method on them. And this method is actually really useful when you're starting off with plotting graphs. Remember, graphs are the picture versions of your functions. So let me call up my calculator, and here it is. And the first thing I'm going to do is press mode, and then press the number 3 to get into table method. And you'll see I have my functional notation. So f of x is the same as saying y is equals to. And I said we were going to plot the parent function, so I want y is equals to x. To get that x, you tap on alpha and then the red x. Okay, press equals to indicate that you are pressing enter. We're not going to do g of x, so I'm just going to press equals again. Now the start is what x input do we want to start with? And I'm going to start with -3. And the end is what is the output I want to end with. I'll end with 5. X is not the output I want to end with, the input I want to end with. And I'm going to end with x is equals to 5. The next question asks what steps I want to go up in. And that means what values of x. I'm going to go up in steps of 3. Let's be different. Press equals and let's see. I've been given 3 coordinates within that space. The first coordinate is 3, -3. Then I've got 0, 0, and then I've got 3, 3. So let's plot those. Now, once again, I'm just going to write y is equals to x over here to indicate that that's the function I'm going to plot. Then I'm going to estimate that this over here is where -3 is, and that makes sense. And then I'm going to go down 3 spaces and make this over here equal to -3. Why? Because my first coordinate is at -3, -3. My second coordinate was at 0, 0. So let's plot that. And my third coordinate was at 3, 3. So I'll just put in the 3 there and the 3 there and plot it. And write down the coordinate. Now this type of plotting method is called the table method, where I have my x values listed as -3, 0, and 3, and my y values is -3, 0, and 3, and then I use those to plot some points. Let's join up those points now, and I'm going to, oh, I did it wrong. We'll just keep it like that. I thought I had selected a ruler, but now I obviously have. Let's go undo and undo. Okay, here's my ruler. So I'm going to draw a line through all my points, and look at that. It's beautiful. A thing of beauty. So the parent function of a linear function is going to go through the coordinate 0, 0. And the reason it goes through the coordinate 0, 0 is because that's the y-intercept for the parent function. If you remember back to grade 9, the y-intercept was indicated by the amount you were adding to the function. Okay, now we're going to look at the parent function of a parabola. And a parabola is the result of a quadratic function. And you've been factorizing quadratics for a while now. And so you'll be familiar with how to work with x squared. There's actually a part of me that's been wondering lately if we haven't been teaching algebra wrong, and I mean we as South Africa. Maybe we should be teaching it from the graph point of view. Because when we solve for x, we're really finding out where are the y-intercepts. Not the y-intercepts, where are the x-intercepts. So when we solve for x, we're finding the x-intercepts. And maybe it would be better to learn it that way. I don't know. But you'll see what I mean as we go further along in this section. So while I'm busy going and doing all of these plotting things, I want you to think about all of that. Okay. So let's go to the next slide. And here is the quadratic function. And the quadratic function has a formula of y is equals to a x squared plus q. Now that is how we learn it in grade 10. So I'm just going to label it over there. In grade 11, we introduce another term. So let's change it to pink, and I'll show you. Y is equals to a x plus p squared plus q. Okay, and just label it so that no one gets scared. That is where we're going to in grade 11. Now, in grade 10, we only move the function up and down. So it's going up and down. And what do you think, which value does it? The q value. But in grade 11, we're able to move it left and right as well. And what's different about the grade 11 function? It's got that p. So surely that p must move it left to right. Anyway, that's not really what we're focusing on at the moment. We're going to focus on the parent function of the quadratic function, which is y is equals to x squared. Now, we can do this using a normal table without too much hassle. We could say x and y, substitute negative 2 in for x, and what is negative 2 squared? It's going to be 4. But this takes quite a bit of time, so I'm going to just go back to my calculator, and I'm going to change this to x squared. There we go. And I'll press equals, and equals again. I'm going to start at negative 2 this time, and I'm going to end at 2, and I'm going to go up in steps of 1. And my table says that for the value of negative 2 for x, I've got a value of 4 for y. And then for negative 1, I've got a value of 1. And then 0, 0 again. So let's draw that over here. I'm going to plot 0, 0. And let's just check what was happening with the other coordinates. Negative 1 and 1. So negative 1 and 1 is over there. And then I've got negative 2 and 4. So negative 2 and 4. 1, 2, 3, 4. Wait, 1, 2, 3, 4. There we go. Negative 2 and 4. But what's happening on the other side? Because this doesn't look like a straight line. And you would be exactly correct if you thought the same thing as me. Let's go down a bit. Oh, and then, and where x is equals to 1, y is equals to 1 as well. So let's draw that in. 1, 1. And then we have 2 and 4. How do I know that? Because I'm a brilliant maths teacher. Also, I've scrolled down on the calculator before and seen that it's 2 and 4. Now, a parabola has a beautiful curve to it. It only has one curve, and it will either be a curve that goes up or down. It'll either be happy or sad. This is the parent graph though, so its y-intercept is equals to 0, and it's going to be happy. Okay, so that is the parent function of the parabola. Now, in your grade 10 and grade 11 syllabus, that's mostly what you'll be working with, the straight line and the parabola. Occasionally we use a hyperbola or an exponential graph just to shake things up a little bit, but generally the questions that are linked to those are more simple. But as soon as you see a parabola question with a straight line, you're probably going to be challenged a little bit in your understanding. What is a hyperbola though? That's the next function we're going to go on to. A hyperbola has one value that's going up and the other value that's going down. That means the relationship is your input variable is in the denominator of a fraction. And that poses some interesting questions, because can you ever divide by 0? No, you can't. And that means there are places on the graph or on the Cartesian plane where the graph cannot exist. Why? Because we can't divide by 0. We can never ever divide by 0. It's just not possible for us. So the graph can't be plotted in that place. Let's go now to see the hyperbola. And the hyperbola has a formula of y is equals to a over x plus q. And once again, it does change a bit when you get to grade 11, but we're not going to go over that now. We're just going to plot the parent function, which will be y is equals to 1 over x. And once again, I am going to use the calculator to do this. So let's start by putting in a fraction, 1 at the top and x at the bottom. And press equals. We're not working with g of x. Let's start at negative 4, and we're going to end at 4. And let's go up in halves. Okay, so our first coordinate is negative 4 and negative a quarter. So we go across on the x-axis to negative 4 and negative a quarter. And I'm not going to label each coordinate. I'm just going to go through them. The next one is negative 3.5 and that other number. Oh, that looks horrible to plot. So let's go to the next one, which is negative 3 and a third, basically. So negative 3 and, oh, let me check. Negative 3 and negative a third. So that's going to be roughly over there. That looks very close, doesn't it? Let's see what happens. At negative 2.5, it goes to negative 4. At negative 2, it goes to negative a half. It's really not changing much, is it? And then it goes to a third, 2/3, negative 2/3, and then negative 1 and negative 1, which is over there. And then it goes down to negative a half and negative 2, which is over there. And then suddenly we have an error. Now that error exists because at this point along here, the function is equals to 0. So this is called the asymptote. And it's got a very funny spelling, but I love saying the word. So this function is going to carry on coming closer and closer to the asymptote, but it's never going to touch it. So I'm going to draw these in. There we go. And what do you notice at the top? It seems to have another asymptote. And that's exactly correct. There's the other asymptote. This asymptote has a formula of y is equals to 0. And this one has a formula of not y is equals to 0, but x. Let's try writing x again. X is equals to 0. Now the hyperbola is divided into two parts because it's got two asymptotes. And the second part, we can start plotting. At 0.5, it's going to be at 2. Can you see how this mirror reflection is going to happen? And then it's going to be here. Let's just go down 1 and then. Oh, it's going to be beautiful and get closer and closer. So it actually has some nice lines of symmetry. Do you remember what a line of symmetry is? It's a line that the graph can be reflected along. For example, this line over here is one that it can be reflected along. This line has the formula of y is equals to x. It's the parent function of the straight line. And can also be reflected along this line. And this has the formula of y is equals to negative x. Now, grade 10s, we've done quite a bit of plotting so far. We still need to plot one more parent function before we get to a problem. And the problem is going to be a word problem. The reason I've chosen a word problem is because I want to show you how useful this actually is and what we actually use functions for in real life. Okay, go and have a break. I'll see you just now. Okay, grade 10s, I don't know about you, but this is actually making me quite tired. There's a lot of information that's coming at you right now. We've plotted 3 different shapes of graphs. We plotted a straight line graph, which is a result of a linear function. We plotted a parabola, which is the result of a quadratic function. Remember the smile or the frown? And then we have plotted a hyperbola, which had the 2 asymptotes, which divided the function into 2 parts. And the hyperbola had the unique characteristic that when the one value went up, the other output value went down. And that was because x was in the denominator. Okay, the last one we need to talk about is when x is in the exponent. Can you guess what this function is going to be called? If you guessed the exponent function, you would be absolutely correct. Mathematicians aren't really known for having huge amounts of creativity when naming things, so we tend to choose names that make sense. So the exponent function has the x in the exponent position. Let's take a look at the formula and then plot the parent function. Now the exponent function has a whole lot of variables in it. It's y is equals to a times b to the power of x plus q. And there are a whole lot of things we need to know. A can be any number, but b must either be between 0 and 1, or it has to be more than 1. But it can't be negative ever, 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 ever. Now, the reason behind this is because A really tells us the position of where it must be. So if it's going to be above the asymptote, then A would be positive. And if it's below the asymptote, then A would be negative. But B can't be 1 because B has an exponent. And any 1 to the exponent of anything is going to give you exactly the same answer, 1. So it has to be either between 0 and 1 or after 1 and going up. So as you can imagine, depending on what B's value is, the graph is going to curve in different directions. But that's for next week. Today we're just going to plot the parent function, and let's do that. Okay, now I've stated that this has an asymptote. It has only one asymptote. We are going to plot the parent function, but we're going to plot it as y is equals to 2 to the power of x. And I'm going to use the calculator. Let's start by clearing what we've done before and make it 2 to the power of, and we press alpha and then x. Whoopsie. Press alpha and then x and equals. And we're going to start at, let's start at -4. And we're going to end at 4. And we're going to go up in halves. And let's see what happens. So our first coordinate is -4 and 0,06. So it's way down over here. Then -3.5 and 0, oh, that's too close. Then -3 and 1,25. So it's over there. It's not much change, is there? Let's go down a bit. -2.5 and it's 0,17. -2 is going to be 1/4, so it's going up slightly. Then -1.5 is 0,35, and -1 suddenly jumps to 1/2. Okay, then we've got -1/2 and it goes to 0,7, and at 0, our y-intercept is actually 1. That's something different. Then we've got at 0,5, it suddenly goes to 1.4, which is roughly over there. And then it goes at 1 to 2, and then let's just skip ahead to 2, it goes to 4. Oh, do you see what's happening? It's increasing exponentially. Now you know where that phrase comes from. I don't think we have enough space. Nope. So let's just plot what we've got over here. So I'm joining up these dots, and I'm hopefully doing a neat enough job to make people feel happy. So it's going to carry on going up and up. But will this line ever cross the x-axis? And the answer is no, because there is an imaginary line going across the x-axis, which is our asymptote. And the asymptote has an equation of y is equals to 0. Okay, grade 10s, before we run out of time, I want to go and look at some word problems so that you can see how we use functions in real life. Now, if you do physics, you'll have seen a question like the one that we're going to do second. But first, let's do the first one, and you've probably seen a question like this in grade 9. But it's important that you recognize the skills that you've used before and how to use them again. Let's take a look. So the first question says, a high school had 1,200 students enrolled in 2004 and 1,500 students in 2016. The student population P grows as a linear function of time T, where T is the number of years after 2004. So that means in 2005, T will equal 1. And in 2006, T would equal 2. Use a graph to determine how many students were enrolled in 2012. Okay, in order to do this question, we need to calculate how many students were enrolled every year. And we've been told that this is a linear function, which means that the same number of students were enrolled every year, consistent amount every year. And we're going to end up with a straight line. Do you see how linear and line come from the same origin, the same word to begin with? How are we going to do that? Do you remember the gradient formula? Well, that's exactly what we're going to use here. We're going to find out what was the total change in students over the total amount of time. Let's do it. So we're going to take, and I'm just going to write over here, m is equals to, and let's say 1,500 minus 1,200 over the number of years, which is going to be 2016 minus 2004. Now, luckily for you, I have a brilliant brain, and I've calculated this already, and it's equals to 25. So that means every year, 25 extra students were enrolled. So in 2005, 25 students were added. In 2006, another 25. 2007, another 25. Now at this point, we could put that information into a graph, and we could plot put it into a table, and we could plot the graph using the table. But I'm going to use the intercept gradient method to plot this graph. In other words, I'm going to show on the graph the increase. Now, if they are getting 25 new students every year, it means that it will take them 4 years to gain 100 students. So I'm going to plot my first point at year 0, where they had 1,200 students, and my second point 100 students later, which means it would be at year 4. And then I'm going to draw the lines. Okay, so going back to our graph, let's start with, let's just make this 200, and then we've got 400, and then we've got 600, and 800, and then we've got, I almost said 1000, but it's 1,000, and then we've got 1,200. Then on our x-axis we have 0, then we have 1 year, 2 years, 3 years, 4, 5, 6, 7, 8, and so on and so forth. So we're starting at year 0 where we have 1,200, and 4 years later we go up by 100 students, and 4 years after that we go up by another 100 students. So let's connect those dots and see what happens. There we go. That should be nice. Okay, now let's figure out when 2008 was. Is it 2008 we need to know? No, 2012. So if this is 2004, then, let's do it in pink. This is 2004, this is 2005, 6, 7, 8, 9, 10, 11, nicely done. At 12, that means this coordinate represents what's happening in year 2012. How many extra students do we have? Well, our graph is telling us we now have a total of 1,400 students. The coordinate is still 8 and 1,400. I just put the 12 there to help me to figure out when it was. Okay, the last question for today is one that I find quite exciting. It's actually more on a grade 11 maths level, but if you're doing physics, you'll recognize this kind of problem. And it's more real life. It's how we can actually see functions in real life. So let's take a look. I'm sure you're dying of suspense right now. And the question says, a ball is thrown straight up from 3 meters above the ground with a velocity of 14 meters per second. The gravity pulls it down, changing its speed by about 5 meters per second. Ignoring air resistance, determine when it hits the ground. Okay, so we have been given 3 bits of information here. We have been given a starting height, so a starting height of 3 meters. We've been told that it's traveling at 14 meters per second. And we have been told that gravity is acting against it at 5 meters per second. So 5 meters per second, pretend I've written it all down over there. How do we set up this equation? Well, I'm going to start by saying let h equal the height. I suppose that makes sense. And in order to find out when it hits the ground, we need to figure out when h is equals to 0. Now, you'll hear that I said when. So that means we're going to work with time. And time is equals to t. Which one of these will be the input variable? Well, the input variable is the independent variable, so it's the thing that will continue to happen without the other one happening. And that means it's going to be time. Okay, so I'm going to set up an equation over here. I'm going to say h is equals to, well, we had a starting height of 3 meters. And the ball is traveling at 14 meters per second. But gravity is acting against it, so we're subtracting it. And it's per second, which means it's t squared. Now this is the kind of equation that's you're not expected to plot. And the reason you're not expected to plot at grade 10 level is because you have that middle term. And that means we're shifting it over a little. So I'm going to use my calculator to help me plot this point by point. Let's clear it all, and I'm just moving the calculator to this side, where we'll go 3 plus 14, and t is kind of like x, so I'm just going to put x in, and then minus 5 and alpha x squared. Now, of course, this is going to form a parabola, and how do I know that? Because it's well, first let me say I'm going to start at 0 and I'm going to end at 6. So I'm starting with 0 seconds and ending with 6 seconds. The reason I know this is going to be a parabola is because it has an x squared. So my first coordinate, where x is equals to 0, y is going to equal, oh, I lost my calculator. Y is going to be equal to 3. So let's put it over there. Then when x is equals to 1, y is equals to 12. Okay, so let's scroll up a little and count to 12. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I will plot my point right over there. Okay, the next one says when x is equals to 2, y is equals to 11. Well, that's interesting. It's starting to go down. When x is equals to 2, y is equals to 11. And then when x is equals to 3, y is equals to 0. Oh, so there's our answer. After 3 seconds, it hits the ground. But remember I said this was a parabola? Let's find out if we can get more of a clear idea of the shape of this. I'm going to change the steps to 0,5 quickly. Steps 0.5 equals, and look, I want to find out what's happening at 1.5. It goes up to 12.75. So at 1.5, it's going up to over, oh, that's bad plot, Helen. Okay, so it's going up to there, which gives me a lovely curve. And this literally is the curve of the ball. And it gets down to over here, and of course it hits the ground, and then it's going to bounce. So at 3 seconds, it hits the ground. Now, grade 10s, I'm quite pleased with the work we've done today, and I'm quite pleased that you've seen how functions can be used in real life and why they're so important to know. Next week, we'll be talking about how changing a and q will change the function. The look of the function, where it is, and all sorts of things like that. Work hard this week, and I look forward to seeing you soon. Goodbye.